Ever wonder why humans can digest starchy potatoes but not grassy hay? The secret lies in alpha versus beta glycosidic linkages, a tiny stereochemical detail with big consequences. In this segment, we'll explore how glucose flips into ring form, what alpha and beta anomers are, and why an alpha versus beta bond makes starch edible, but cellulose fiber indigestible. Let's start with glucose cyclization. In its linear form, D-glucose is an aldohexose, a 6-carbon sugar with an aldehyde at C1. In a solution, this linear form doesn't last long. The molecule undergoes an intramolecular reaction. The hydroxyl on carbon 5 attacks the aldehyde carbon, C1, forming a 6-membered ring, a pyranose. This reaction creates a new chiral center at C1, known as the anomeric carbon. The result, you ask? Glucose exists mostly as a ring, and less than 1% stays as an open chain. Now here's where alpha and beta come in. When the ring forms, the hydroxyl on the anomeric carbon can end up in two positions, either on the same side as the CH2OH group at C6, or the opposite side. These two are called anomers. If the OH at C1 is on the opposite face of the ring as the CH2OH, for D-glucose, that means the OH is drawn down trans to C6, it's the alpha anomer. If the OH is on the same side, both up, cis to C6, it's the beta anomer. For D-glucose in water, about 36% is alpha and 64% is beta at equilibrium. The beta form is a bit more stable because it can adopt a conformation where all bulky groups are in equatorial positions. The anomeric carbon is special. In a free sugar, the alpha and beta forms interconvert, a process called mutarotation, via the open chain form. But once this carbon forms a bond to another molecule, a glycosidic bond, its configuration gets locked. A glycosidic linkage is basically an acetyl or ketol bond formed between the anomeric hydroxyl of one sugar and a hydroxyl on another sugar or another compound. If the anomeric OH was alpha, we get an alpha glycosidic bond. If it was beta, we get a beta glycosidic bond. In naming, we also specify which carbons are connected. For example, alpha 1,4 means there's an alpha bond from C1 of one sugar to the C4 of the next. So why do we care about alpha versus beta links? Because this subtle stereochemistry dramatically affects a polymer's shape and our ability to break it down. Let's compare two glucose disaccharides. Maltose, glucose alpha 1 of 4, glucose, versus cellobiose, glucose beta 1,4, glucose. In the alpha linkage, like maltose, the bond angles cause the polymer chain to coil into a helix and bend. Enzymes like amylase in our saliva and pancreas can easily attack these alpha 1,4 bonds. In the beta linkage, like cellobiose, the repeating unit of cellulose, the bonds make the chain straight and rigid, allowing strands to align tightly and crystallize. Our enzymes cannot hydrolyze beta 1,4 links in cellulose. We simply lack the right tool. Although both starch and cellulose are polymers of glucose, we can eat potatoes, starch with alpha links, but not grass, cellulose with beta links. Certain microbes produce cellulase to break beta links, which is why cows, with the help of gut bacteria, can digest grass, and termites can munch wood. This difference is more than diet. It's biology's way of diversification. Alpha-linked glucose polymers, like starch and glycogen, serve as energy storage, easily mobilized. Beta-linked polymers, like cellulose, serve as structural support in plant cell walls, tough and insoluble. The stereochemistry even affects reactivity. For example, cellulose's tight beta-link structure is so tough, it's used to make cotton fibers and wood, whereas starch's alpha-linked coils are less ordered and more water accessible. In real life, this means starch in your bread breaks down into glucose in your body, but cellulose, fiber, just passes through, though it aids digestion as fiber. Another example, Lactose in milk is a beta-1,4 link between galactose and glucose. Many adults lack enough lactase enzyme to break it, leading to lactose intolerance. So, a simple flip of an OH group, alpha versus beta, can decide if a carbohydrate becomes dinner or dietary fiber. In summary, alpha and beta glycosidic linkages originate from how glucose rings form. This tiny stereochemical twist at the anomeric carbon dictates the 3D shape of polysaccharides and whether our enzymes can attack them. It's an example of structure-function relationship. The alpha versus beta glycosidic linkage is the difference between energy fuel like starch and structural matter like cellulose. Truly, a small change with a big impact on biology. Now keep this all in mind as we explore specific carbs next.